Okay, so welcome back, everyone. We are ready to move on for this first afternoon session of the Introduction to Quantum Computing School, Cinega Academy. Let's wait another, 5 minutes, and then we resume. So, till now, is everything clear? Is everything okay? Did you manage to calculate the exercise? Yes, you're right. I'm reading online slides would be great. It's hard to remember all the gates. Yes, you're right. I will put it online this evening. Sorry, this is the first edition of the school. But if you Google the gates, you can retrieve them very easily. For example, here it's sufficient to Google CNOT gate. I don't know if you can find the reverse CNOT gate. Maybe yes. Thanks. Oh, good. Perfect, Karim. Yes. There's also the reversed CNOT gate here. Let me see. No, I think not. But okay, it's not a problem. Okay. No. Reversed CNOT is not here. Okay. Let's resume the lesson. So, for this exercise, fantastic. Felix found also the reversed CNOT gate. Perfect. Thanks, Felix. So, for the exercise, okay, what we have to do? We have the system composed with these two qubits. Then we apply a first CNOT gate, then we apply a reversed CNOT gate, then we apply a CNOT gate again. So this is the order of the application. Remember that the order is always from left to right. Okay, from up to downwards, from left to right. And this is the solution. So we apply, the first thing that we apply is this one. Remember that I cannot see your screen, only your webcam is normal. Do you see my screen, everybody? It says that is UC5, okay. Nope. Yes, somebody yes, somebody no. Is this quantistic? Strange. Okay. I don't know what to do because half of you say yes, half of you say no. So maybe I can try to interrupt the sharing and do it again. I don't know. Okay, perfect. It was a problem of the screen thumbnail. Okay, thanks. Good. So we were saying That remember that in this case it is the same because we have the same gate at the beginning and at the end of the circuit. But remember always that at the contrary, the first gate that is applied to the system of qubits is the first one on the left. But when you calculate the total quantum gate, that is the result of the multiplication of the gates acting on the system of qubits, you have to start from the right, of course, because this here there is the vector. So the first gate that we apply to the vector is this one. Okay, that is this one, that is the first one. Then you apply the reverse C0, then you apply another time the C0 gate. Multiplying it, you will obtain this gate here. Do you recognize this gate? Do you remember a little about what we were saying before? This is a swap gate. So with this simple exercise, we demonstrate the equivalence between the application of these three CNOT gates, two normal CNOT gate and a reverse CNOT gate. This circuit here is equivalent of a swap gate, the equivalent of a swap gate, okay? So it was only a little exercise. Perfect. So, okay, now something really important. Before going into the second argument of our lesson, these real quantum computers, I want to make sure that you will be able to do the exercises that are preventivated for the final part of the course. So I will load another set of slides. Let me do this in a moment. Okay. Perfect. So now let's configure your devices in order to use our Jupyter notebooks to make the exercise for the rest of the course. Okay. So what do you have to do? First thing that you have to do, you read the mail that was saying that you need a bash for this part of the course. First of all, you need to register, to take note of your username. This part is only for the students because we have not a big number of accounts for the exercise part. So in the next slide, I will say who is who. But right now, you have to write your username, that is this username here. You have to replace the symbols with your number that I will tell you in the next slide, and take note for the password that is the same for all the accounts. Please, when you log in for the first time on your account, that is this command here, SSH without login, is SSH A08TRC, your number, at login.marconi.sinega.it. When you log in for the first time, use the command passwd to change your password, okay? So this is the number associated to your name. Please write it down. I wait, I don't know, 1 or 2 minutes. And then you have to do something. So be ready with your password, with your number, and with your bash. Okay? This is for activating the environment that will allows you to use our Jupyter notebooks on our systems. You are not on the list. Yes, because this is only the list of the students, official students that we selected. I guess that you are a listener, not a student. Okay. Can I move on? Is everybody?
Yeah, sorry, Daniela.
Has
Oh, yeah,
taken
okay,
note?
great. That's what I wanted.
Yes,
Just that.
of course. Okay. Okay. So let's begin. Previous slide. Yes, of course. So I can write it something here. Okay. Now, let's do this. So, let me do a little thing. Okay. I will copy these comments on chat for your commodity. Oh, it's huge. Okay. Very huge. Okay, now on your local machine, run this git clone command. And then go to the directory that you just downloaded. Okay. So for using our Jupyter notebook, we have to use a script that allows us to use it on our local machine. To use it, it's recommended to pair your keys with our supercomputer Marconi. It is an easy task. What you have to do is to write on your local machine, so on your bash, you have to write these commands here. First command is SSH keygen. The second command is an SSH copy ID towards your account into the Marconi supercomputer. Okay, so SSH keygen will ask you something. If it will ask you to overwrite something, say yes, and leave blank everything else. Passphrase, original address of the key, everything as default. When you complete the SSH keygen, you have to copy your ID toward your account on Marconi with the second command. Okay. It will ask you the password, your password. Remember your password, I wrote it in the chat, use it. If you changed it, use your current password, of course. Okay. Did you manage it? Is there any problem?
Please wait. I have a problem with Git. I have a problem with Git clone because.
Let's do the second step.
Could you hear me?
Now you have to log to your account. This time, if everything is made corrected, if everything is good, is right, the system will not ask you for the password because you pair your password in one way. Now you're pairing in the reverse way from your account to your local computer. So after, you have to make almost the same steps that you did on your local machine. So you have to call SSH keygen with the same philosophy of before, leave everything blank and overwrite if it asks you to overwrite something. This time, you have to launch SSH copy ID localhost. It will ask you for your password again, and then the procedure is done.
Sorry, could you repeat which is the
While
password?
you are on the machine, the remote machine Marconi, you have to clone this repository on your home. Federica is asking if it's possible to work also on local machine. Yes, it's possible, but you need some particular environment because we are using Python environments for Ocean software, that is the D-Wave software. This time we are using Qiskit, and I don't know if anything else for the lesson of Marco Ballarin. So it's possible, but it's a little bit hard because you have to install a lot of things. Alexei? I see that
you hear me? I think I have a problem even with
Alexei,
even.
I can't hear you.
Could you hear me now? Could you hear me? Can you hear me?
I cannot hear you. No, no. See if it's my problem.
Can you hear me?
Okay, maybe it was my problem. Try again.
Can you hear me?
Yes, yes, now yes. Sorry, it was my problem. Tell
Okay.
me.
I have a problem even with Git clone. So I wrote the path from this path, and it's asked me username and then password, and it doesn't accept the password, but I have changed it.
It's asking username and password when you are
Git clone.
using Git clone.
Yes.
Strange.
So I entered to Marconi, using SSH, the first line, and then I tried to use Git clone.
And it's asking you a password.
Yes.
It's a little bit strange because it's an open repository. Anybody
that
else
happens when
problem?
That happens when you made a mistake in the copy paste. It happened to me. I typed introduction to GC school instead of QC school, and I was asking for a password.
Okay, thank you. Thanks a lot.
Introduction to, and then what is this letter? What does it? I don't see. Is it G or
QC school?
QC school, yeah. So it's correct. It should work. But
it's strange. I try myself right now. Maybe.
No, now it's possibly it's well. Excuse me.
Do you see my terminal?
Yes.
Okay, let's make a try. Git clone. Yes. not asking password. This is how it's gonna be. On the slides on Marconi only on your local machine too. On your local machine, you have to do SSH keygen and SSH copy ID as.
No, I think I succeeded. So it was a problem with the with some letter in the line. So what should I do now? Excuse me if I am asking you again. So now I have a folder forward to.
Okay, now you have a folder on your local machine, right?
No, I did it on Marconi. So I am
so
inside
you have to do the same thing also on your local machine. Did you manage to pair the keys with Marconi?
No, not yet. So I need to git clone on my local machine, right?
Yes. You have to call git clone both on your local machine and on Marconi.
Okay.
On your local machine.
Okay, done.
Okay, the previous slide. Wait a moment. Okay. So on your local machine, you have to run git clone, then go to the forward to directory.
Okay, done.
And then you have to call SSH keygen, this command here.
Okay.
Don't worry, this is a procedure that we have to do only today. Or this is valid for every season, every exercise season that we will have during the school. So you have to call SSH keygen, and then when the key is created, you have to do SSH copy ID and your address on Marconi.
Okay, okay. Now I am at the last line. So if it works, I think. Let me check.
Yes.
Marconi Chineka point it. Okay. Okay, number of case added 1. I think it works, right?
Oh,
now
what did he say to you? Now, for verifying if it works, it worked. Try to do this. Try to do SSH and your address on Marconi. It will be not asking for your password. You will enter without using your password. Is it right?
yeah, now one moment, I'm trying.
Don't worry.
Okay, it's entered without password. Yeah,
But
it's
now you have to complete the process. Now you are on Marconi.
yes.
Complete the process, calling again SSH keygen.
Yes.
The same procedure as before.
Okay.
And then do an SSH copy ID. This time you have to write localhost instead of the address of Marconi.
It asks password of localhost.
Yes, now it's normal. Use your password.
Okay. My password on Marconi.
Yes, yes.
Okay, number of keys added 1. Now try login into the machine with SSH localhost and check to make sure that only the case.
Okay, it's done. This is a standard message. It's done. You can now that you are on Marconi, complete the procedure downloading with the kit clone the introduction to QC school directory, and write down. I will write it for you in chat in a moment. Write down this address here that we will use it for the Jupyter notebook. Of course, as usual, you have to replace these symbols with your number. Okay.
Sorry, me too.
Yes.
I have one problem when I try to do SSH copy the localhost. It asks for a password.
Mm-hmm. This is the Marconi password.
Yeah, I put the one in the chat, but it says that it is the permission is denied.
Strange. Are you sure that is the right password? That you write the password right?
I can
Maybe try again, because I think there is a problem of.
So normally, sometimes when you connect the first time and you didn't manage to connect, you have to add the -O identities only equal to yes in the SSH command. Maybe I'm going to copy it in the chat.
The -O, sorry? I don't understand. Didn't understood the question. What is the -O? Let's try to do one thing. I cannot. Okay. I just break the recipe. Yes. I don't know if this -O identities only is required, but I never used it.
Sorry, after the access to localhost, we have to download the repository again?
Yes.
Okay.
Repository has to be downloaded both on your local machine and on Marconi.
Daniele, I did just this. I cloned the repo both on Marconi and locally. But when I do SSH keygen on my local machine without password, no problem. I generate the code. I mean the certificates. But then when I do SSH -copy-ID and the Marconi address with my 2 numbers, it throws me basically a couple of errors saying that the somebody's doing something nasty on the remote system, and I cannot copy the ID onto.
Okay, it's a problem that I have heard before, because there is something strange on your SSH file. The solution is to delete a line. Try to It's something that is not related to the. It happens maybe when you have some other keys stored on your machine or something like that. Let me see.
I have many keys on my machine indeed, but what line should I delete? What is it?
I don't remember. It's the funny. Maybe it's is the error telling you that a particular line is offending? No host. Yes, Sergey. Thank you.
Remove the lines from known hosts.
Yes,
Okay.
try the solution from Sergey.
Okay.
Yes, Sergey also is suggesting to keep a copy. No host.
Me instead, when I downloaded the game, I cloned the game from GitHub. It gives me an error. RPC failed.
Sorry, what? No, I didn't want you.
When I try to download again the repository, it gives me an error. RPC failed. Result 22. The remote and hung up unexpectedly.
Oh, so it's a forest of fantastic errors that I've met. Try again. Maybe it was a temporary mistake. I don't know.
Yeah, I already tried 2 times. Actually.
2 times it's the same.
Yeah.
No, the fun fact is that I tried on all the accounts this procedure. It was. Let me Google your error. Maybe.
Maybe I write it in the chat.
Yes, thank you. Control, if the command is right, do some. Introduction to ITQC school, okay. Probably, yes.
Okay, so maybe it's a very stupid thing.
99% is, but
yeah, okay,
don't worry, but my working life is a series of stupid things. It's very, very common and normal. Introduction, the directory is right. So, Matilde, did you manage?
Yes, I solved it. Was just that I had to add the git at the end.
Oh, perfect. Fantastic. Thanks. Okay. Now, so the last thing I put the chat, if everybody have done, is this address. Copy it and replace the hashtags in English with your number. Because now there is the last part. That is this one. copy this command here. For launching this command, you have to be in the forward to directory. That is a subdirectory of the introduction to QC School that you've just downloaded with Git. So go back to your local machine, not on Marconi. We will use Marconi through your local machine, okay? So go back to your local machine. Go to your local directory, introduction to QC School, and to the forward to directory. Now, try this command. This is the command that allows you to use Jupyter Notebook. What do you have to do to use this command? You have to replace, as usual, these hashtags with your number, here and here. Okay? I assume that you all downloaded the Git repository on Marconi into your home. If it's not, correct this address. But if you download the repository on your home, this address is correct. Okay? So, now, your port number for the session and the future session of the school will be 32000 plus your number. Okay? 320 and your number. So replace your port number with your port number and replace the env name. You see, these are two different things. Replace env name with MPS. This one. Okay. Finally, replace dir name ES here with this one, MPS dash Jupyter, and try to run this code. It will open a web page with the notebook on your local machine using your preferred browser. If the URL is not working, it can be because there is a passage of there that cannot work. Just quit it with Ctrl+C, confirming with a yes, and relaunch it. It will work if everything is correct. Okay, so if you manage to do this, you can make all the exercise for the lesson without installing anything on your computer. If you want, maybe for the next lessons, today it is only an example. A little Jupyter notebook that is an example for the MPS part of the lesson that will be held from Marco Ballarin in an hour. Localhost kgen should have been done on local machine on Marconi. On Marconi. This is on Marconi. You have to do connection file, connection refused. It's a good thing. Try again. It's a sign that this is working. There are several attempts to get a token and say not ready is normal. Let's wait a little bit. It's normal because we are a lot of people that are trying to use it together, but I've made a lot of tries. I can assure you that it will work.
Can I ask a question? Sorry.
Yes, of course.
Yes. Sorry again. Is forward to a script or a command? Because it seems like it is on the first line up there on the slide. It says
It's a script.
The script, okay.
Yes.
And that script is within the subdirectory forward to?
Yes. Yeah.
Oh, okay.
Excellent.
Right. Thank you.
You're welcome. So, Rodolfo is asking as an auditor, how can I download for GitLab? Which account and password should I use? My own account of Marconi. If you are going to use your own account on Marconi, as Mark was saying, you can download it without password or ID, and you have to pair your account, your Marconi account, with your local machine. Sergey, permission denied. About what? No problem. About, I think, forward to. It's strange because permission denied means that maybe you did not, but you can enter on your Marconi account without using a password, right? I get it. Okay. Okay, fantastic. Perfect. Channel 1 open file connection failed is normal. Try again. Control C. Kill the execution of the Jupyter notebook and do it again.
Mia, I get these instructions at the end of the command, but I cannot open this link apparently.
Why?
It doesn't give me the web page.
Try to, okay, you copy this link, you copy this link and you pasted it on a browser, right?
Yes.
And it says there is no page available.
Yeah.
Try again.
No, it leads me to the Firefox main page. So it doesn't open it if I click on it.
Strange. Try to copy and paste instead of click.
Okay, I seem to have a problem again, Daniela. Sorry.
Don't worry,
It's just a sin. It never ends. All right. I'm within forward to. I do the forward to script. And then the second line that you showed here is a directory in which I have to go to.
No, this is the part of the same command.
Okay.
Sorry, because it was not
in
automatic retard. Because
I get it. For the future, if I may make a suggestion, you should make sure that people understand this is actually a command. So put a $sign at the beginning or something to signify the prompt, and at the end of the first line, put a backslash. Space backslash, so we know that it's a following line. I didn't know what it was. Okay.
Yes,
great.
You're right. Thanks for your suggestion, because it's really precious to me, because I was saying this is the first edition. A lot of things can be better. You receive the following lesson.
Mia, I didn't solve it. It cannot find this link.
You cannot find something. Sorry.
It seems like this link doesn't exist.
This link doesn't exist. Try again. Try to kill the notebook and relaunch forward shoe.
Okay.
Excuse me, in my case, yeah, I think I came to the same path, instructions, open a browser, add, and the link. And I have the message also localhost contacted, waiting for reply. It's not in terminal, is in the menu, how to say, the pop-up message of my system. And I trying to put this link, and it's trying to connect, but it writes waiting for localhost.
Okay. Let's kill the forward to application and try to run it again.
It is normal that when we put the forward command, it asks for the password many times.
No, it's because maybe you did wrong the pairing of your keys.
Okay.
May try to redo these steps here. So don't worry, but right now this is only a try. This evening I will upload these slides on server, so maybe you can continue to try. Now let's do it for another 3 minutes right now. But just for curiosity, can you raise your hand if you manage to open the Jupyter Notebook? Okay. Only one?
Sorry, I have a question.
Yes.
I do receive this message that there is an active job which I should cancel because I've done many trials. How should I cancel it?
It says the command. It also
It
says
says that there is a found existing job for MTS.
yes, and then it says something like
with the job number.
SSH. There is a command.
Okay. So I should execute this command here.
Yes. Yes.
Okay, thank you.
No problem. Okay. Let's wait another couple of minutes, and then we move on. The second part of the lesson. Yes, it's time.
Renata.
And I will give you these slides I was saying this evening on the repository, and you can use them, I don't know, this night or tomorrow in the morning to try to open this Jupyter Notebook. Okay. Anything else you want to ask before we move on?
Well, excuse me. In my case, it's waiting. It's waiting, but it's waiting already a lot of time.
This is normal because our supercomputer are really busy. So
Okay.
this is not.
Is it possible to launch the same thing on a local machine? Just open a Jupyter notebook
Yes,
on a
yes, it's
local.
possible. Yes, it's possible, but we have to install something. If you want, I can give you this evening, in addition to the slides, I can give you also a script that can install a virtual environment of everything that we will do. So you can use also your local machines.
I mean,
Sorry.
I have already Jupyter notebook installed. I have Honda. I have Python. So what I need more? Git possibly, right?
Yes, sorry.
So I mean, at my local machine, I have Python installed. I have Honda installed. I have Jupyter notebook installed. So what do I need?
You have to realize a virtual environment if you want, and you have to install something like Qiskit, like Ocean, SDK, that are packages created for using quantum computers.
Okay, thank you. I think it could be useful to have it on local machine.
Perfect. So this evening I will also give you the instruction to install the necessary things on your local machine. So you can choose to use your local machine or this Jupyter notebook on our machines. So let's go with this second part of the lesson.
Can I just say a thing really quickly, Daniela?
Yes?
Also for the auditors, I think you should clone the Git repository, because even though you don't have access to Sineca resources, you will still have access to the Jupyter notebooks that will be made ready by us. I mean, like the one for today, it is already uploaded, and I think in the following days they will be uploaded in the same repository.
Thank you, Marco. Yes. Good point. Okay. Okay, so let's resume. Perfect. Okay. I will send you the instructions. So let's take back our speech about quantum computing. So last slide we saw the Deutsche algorithm and how we can use quantum algorithm and in particular quantum parallelism to create computers that create quantum algorithms that are more powerful, exponentially powerful, respect to the classical ones. So what is a speed up? Okay. So speed up is something related to the compilation order of an algorithm. Measure the operation of the number of operations. It measures the number of operations required to solve a given problem. It's usually expressed as a function of the size of the problem to be solved. Okay. So we have two types of speed up that we can achieve with quantum computing. Polynomial speed up and exponential speed up. Polynomial speed up means that the order of the number of operations needed to solve a certain problem is polynomially smaller. So for example, we pass from n operation to square root of n operation. An exponential speed up instead is an algorithm where we can use an exponentially smaller number of operations to solve a problem. For example, we can, for example, if we go to n operation to logarithm of n operations. In terms of number of operations, this difference is huge. For example, in this graph here, we can say that we can see that if we compare these three different order of complexity, we can easily see that when n is growing a lot, also the other two lines are growing, but not with the same number, because if at n equal 100 we have 100 operation for the n algorithm, only 10 for the square root and 7 for the logarithmic part, at the end of the graphic the difference is very huge, because 100,000 operation versus 300 operations versus only 17 operations for the exponential speedup algorithm. Okay, this is what we mean when we say that an algorithm has an exponential or polynomial speedup respect to another. So let's give you a brief timeline of quantum algorithms. We can begin this timeline with the description made by David Deutsch, the Deutsch of the algorithm that we've seen before, that describes the first universal quantum computer. In 1994, we saw the first real exponential speed-up quantum algorithm, the Shor algorithm. In 1994, Peter Shor invents a quantum algorithm for factorizing semi-prime, the famous Shor algorithm. It guarantees an exponential speed-up. Now, let's go to 1996, when Lovegrover invents the quantum search algorithm in a database. It will assure polynomial speedup. In 1997, we have the Hamiltonian simulation algorithm to simulate the evolution of a quantum system on a quantum computer, exponential speedup. 2009, HHL algorithm, exponential speedup for solving system or linear equation. These are a restricted selection of the most important quantum algorithms that were created during the last years. Let's see very quickly what the algorithm, the Shor algorithm is, not the algorithm in itself, because Riccardo will show you tomorrow the nature of the algorithm. We will show only the problem that it solves. The problem is related to the asymmetric encryption. How we protect our data? Right now, with asymmetric encryption cryptography, our data is protected in this way. We have, for our messages, we have a public key and a private key. The public key is something that is known by everybody. Okay, you can use my public key to send me an encrypted message. But the other part is the private key. It is something that is private. My private key, I am the only owner, I hope, of my private key. So if you send me a message encrypted with my public key, I can decrypt it using my private key. Okay, this is the scheme of the asymmetric encryption algorithm. Theoretically, is it possible to extrapolate the private key from the public key, because it's the private key is mathematically encrypted inside the public key. So there is a risk that somebody can guess my private key by looking at my public key. But in practice, it's not that simple, because this protection is entrusted to a class of mathematical problems that are very difficult to solve. So we trust on this. An example is given by the factoring of semi-prime numbers. So given a number n, find two prime numbers, P and Q, such that n is the product of P and Q. Okay, they are all problems of exponential computational order. What it means? It means that if you increase the number of digits of the n number that you want to factorize, you will increase exponentially the number of operations that you need to factorize it. For example, for a 300 digits number, it will take 3 to the times 10 to the 28 operation to solve this problem. Summit, the most powerful supercomputer in the world, performs only 2 times 10 to the 17 operation per second, making 3.10 to the 28 will cost about 4,700 years. It's not impossible, but it's practically impossible to solve it. Okay. Now, with a Shor algorithm. In 1994, Peter Shor invents his algorithm. His algorithm is able to solve all the problems used to protect private keys, including the factorization of semi-prime number. This is belonging to the category of exponential speed-up quantum algorithms. We can see that the number of operations needed to the Shor algorithm to factorize a key composed of 300 digits is only 3 times 10 to the 8 operations. So if Summit could run Shor's algorithm, it would take just 1.5 nanoseconds to factor a number consisting of 300 digits. It is not only the important thing. The important thing is that the computational order of the Shor algorithm is linear, is polynomial, is not exponential. So maybe with the exponential order algorithms to solve a problem of this kind, I can raise the number of digits of the number that I want to factorize or not to factorize, and I will increase the complexity of the problem really much. With the quantum algorithm, the Shor quantum algorithm, this is not true because it's growing linear, and if I raise the number of digits, it will be not sufficient because the complexity of the algorithm is the problem is not so much elevated. Okay, so far we have seen how quantum computing works mathematically. Okay, so we have discovered that it's possible to exploit a certain phenomenon, in particular quantum parallelism, to build quantum algorithm capable of solving some types of problem exponentially faster. Example of Deutsch algorithm made us begin to understand the power of quantum parallelism, and we briefly mentioned also the existence of other quantum algorithms that has this exponential speed up. A question arises: why today? We know that today quantum computers are a real thing, and why are still not used to implement the most powerful algorithms? The answer is simple. Today's quantum computers are not advanced enough. They are much more like advanced prototypes than production machines. But be aware, because first of all, the current machines don't have enough qubits right now to implement meaningful problems using the algorithm mentioned before. But be aware, because the number of qubits is not the only problem that limits the use of current quantum computers. Okay. As you can imagine, building quantum computers is not an easy task. There are many problems to overcome. So let's see how to get an idea of the actual power of a quantum computer, of a real quantum computer today. So the first thing that we have to look when we try to evaluate the effectiveness of a real quantum computer is, of course, the number of qubits. It's trivial, but it's a real thing that we have to consider. It's not the only thing, but a thing. We will see shortly. So far, the most powerful general purpose quantum computers do not exceed the 100 qubits. It's a very low number for a universal quantum computer, but we have to remember that bigger and bigger models keep coming out. So the next milestone, which seems to be to apply to everyone in this field, is to reach 1,000 qubits in 2023. Okay. So this year we will see the first chipset with more than 100 qubits. If the roadmaps are right, in 2 years, in another 2 years, we will see chipset composed by 1,000 of qubits. The second thing that we need to observe when dealing with a real quantum computer is the connectivity between its qubits. Because in quantum computing, as a mathematical science, we never talk about the possibility that two qubits are not connected to each other. What this means? In practice, if two or more qubits are not connected to each other, it's not possible to perform quantum gates involving them together. Not possible physically. In these cases, it's necessary to alter the quantum circuit to adapt it to the needs of the machine being used. Okay, so you have to adapt your algorithm to the machine, to the architecture of the machine. It's a quantum compilation, if you think about it. And a quantum compilation is something like that. So suppose that we want to apply these G gates, these generic G gates to these two qubits, C0 and C12. In the figure here, we see that here there is C0 and here there is C12. They are not connected, okay? But they can be connected through these other qubits. So what I can do is this. I can use a series of swap gates to swap the quantum gate, the quantum state of C0, and giving it to the quantum state of C17 that is connected to C12. Okay, so I will pass the quantum state of C0 through C6, through C11, and through C17, and then I can apply my quantum gate. Okay, perfect. So the third thing that we have to take into consideration, that is also totally absent on paper, is the problem of the decoherence of the superposition states. What is decoherence? Quantum superposition states are extremely fragile states, okay? In order to be maintained for a sufficiently long time, it's necessary that the quantum computer is protected from practically any form of noise. Remember that if the qubits are not in a superposition state in a quantum computer, you cannot apply a quantum algorithm. So you have to maintain the state of coherence for a long time as possible. So even the qubit themselves contribute to producing noise capable of destroying quantum states. It's a very hard problem. This is one of the reasons why it's difficult to make large chipset. Okay. So how can the problem be addressed? In many ways. So one way is to isolate the QPU from outside world as much as possible. Another way is to improve the technology of for the realization of qubits. What is so coherence time decoherence phenomena are expressed in data sheets of of quantum computers with these two values, T1 and T2. So with T1, we intend the medium energy relaxation time or the polarization time. So the medium time, so the event that the qubit will pass itself from the 0 state to the 1 state in a spontaneous way. This event can appear with probability with an exponential distribution of parameter 1 over T1. So T1 is the medium time when we can expect an error like that. This kind of error will destroy the quantum state and we will re-prepare the state again. Another error that can occur during the calculation that can destroy the quantum state is the defuzzing event and is indicated by T2. That is the defuzzing time. This other mistake, so the error is the phasing of the qubit. Okay, so they are errors that can destroy coherence of the system. The first thing that to consider is the application of quantum gates to qubit circuits, because there are several techniques used to physically build a quantum gate. The first thing that you have to keep in mind is when thinking about a real quantum computer, that not all quantum gates may be available for a certain hardware. Maybe for a certain hardware they realized, I don't know, the CNOT gate, but they didn't realize the swap gate. Strange, but it's possible. In addition, they have an application time, so they are not instantaneous. Okay, this time is important because affects the time that you can use to program a quantum, to run a quantum algorithm. So remember, the time available to complete a quantum circuit is not infinite, but quite the opposite. The quantum computer works as long as it can maintain its superposition state. Remember always this thing. Last but not least, the application of quantum gates are not free of error. So there is a very important problem. To have a reliable quantum computer, the error percentage on application of the gates must be 0. Okay, so if I apply a gate that rotate my qubit of 90 degrees, okay, there is a possibility that this gate can be wrong and can rotate my qubit of 88 degrees or 92. This is not the same thing. The quantum algorithm will be affected by this error, but we have to take it into account. So, in reality, the error on single qubits is not 0. They're working on it, they're improving it every year, but it's still not 0. It's something like 99.92% or something like that. This is the scale of the order of the numbers. There exists some way to correct algorithmically the errors on a qubit, but they require an exaggerated number of the additional qubits for correcting a single qubit. Okay, so in this case, we can see the quantum error code correction, the short quantum error code correction. And this algorithm uses 1, 2, 3, 8 additional qubit to represent one single qubit. So to make corrected qubits using the error code correction, the short error code correction code, we have to divide our chipset by 9. Okay, and this can be a problem. Okay, so on May 14, 2021, Google made public the technical characteristics of its latest quantum computer, Sycamore. Okay, or Sycamore. Sycamore is a very important machine in the history of quantum computers because it was the first computer to achieve an early form of quantum supremacy in October 2019. So be aware, this does not mean that Sycamore is more powerful than any supercomputer in the world. I can only say that the quantum supremacy achieved by Google is related to the implementation of a particular sampling algorithm, not every algorithm, only a particular sampling algorithm. In the implementation of this particular algorithm, Sycamore also beat Summit, but only in the implementation of this particular sampling algorithm, okay? But it's something, so local quantum supremacy. So let's take a look of the power of Sycamore using these technical characteristics here.
the first thing that we see is the topology of Sycamore. So I say that a real quantum computer has no all connected qubits, okay, but they are connected only on certain other qubits. This is the topology of Sycamore. Sycamore has a chipset of 53 qubits, okay, and this is the topology, the 2D topology. So going on, we can see here that the qubits of possible qubits operation are, for example, a single qubits gate that are Z and XZ, and two qubits gate that are CZ in development, an iswap, a square root of iswap, and a Sycamore characteristic gate. Okay. Here in the duration column, you can see the application time of this quantum gate. So applying a physical Z on a qubit on Sycamore will take 20 nanoseconds. Here there is the error rate. Okay, so for a single qubit gate and for two qubits gate, you can read here the percentage of the error. Here there is another type of error, that is readout error for 0 for 1, or the error that you make when you read 1 where it's 0 and vice versa. And at the last, we have the relaxation time, that is yes, this is one of the time that we use to calculate our coherence time, that is of the order of 15 microseconds in average, maximum 21 microseconds. Okay. So, what is quantum volume? Quantum volume is a metric that can be used to express the power of a quantum computer. So we saw in the previous slides that the number of qubits is not sufficient to say if a quantum computer is good or not. Because I may have a 1 million qubit quantum computer, but if it's full of errors and have a coherence time very low, very low connectivity, is almost useless. So there is a lot of attempts to realize a unique metric to measure the power of quantum computers. One of these attempts is the quantum volume. It was developed by the IBM research and tried to enclose all the key characteristics of quantum computer in a single value. In particular, it takes into account connectivity, number of qubits, and error rates. Okay? So, this is not a quantity that is intuitive to calculate, because this is the formula that we have to use to calculate it, where n is the number of the, where you have to consider of the subset, the possible subset of qubits in your circuit, and n is the number of qubits in a single subset. The n is the depth of the maximum quantum circuit that you can realize with this subset. Okay, so it's not official. There's not official power calibration of the quantum computers, but it's something that it can be used. Okay, now qubits in real life. So we saw that a qubit is perfect as a mathematical object. So we have something that has these particular properties, and how can we realize a qubit in real life? There are a lot of ways. The most used one is the superconducting technologies, but we also have
machines with neutral atoms, trapped ions atoms, photonic technology, and diamond centers technology. The topological technology is something strange because it's a very interesting technology, but they have not proved the existence of the quasi-particles that we need to realize topological qubits in the reality. They don't know if they exist or not, but if they exist, they are really, really good. So let's analyze the first technology that is also the most widespread, or in other words, the superconducting qubits technology. Superconducting qubits are macroscopic rings of superconducting material crossed by electrical current, okay? The states 0 and 1 are identified with the flow of the electric current. So, clockwise, we have the 0 state, counterclockwise, we have the 1 state. The material with which they are made, called niobium, is a superconducting material which, if cooled to temperature close to absolute 0 Kelvin, of course, it becomes able to be crossed by electric current in both directions at the same time. So it manifests quantum behaviors despite the fact that it is a macroscopic object. In this way, the superconducting qubit is able to reproduce to be a qubit, because if the current is circulating in both senses in the same time, we can say that at the same time this qubit is in state 0 and in state 1. The biggest company that uses superconducting qubit is IBM. IBM Q, that is a quantum division of IBM, is an American big tech, is already owner of the most powerful consumer computer in the world, that is Summit, and it was one of the first large companies to seriously embark on the development of quantum computer. In 2016, they created IBM Quantum Experience, that is a website where anybody can use their smallest quantum computers made available for free for the public. Their smallest quantum computers has 5 and 16 qubits. Their largest quantum computer is Manhattan, that is formed by 65 qubits. Okay, they have a very aggressive roadmap. As I say, they predict to have 1,000 qubits in 2023. This is some information about quantum computers of IBM. We see the topology of Manhattan just under the logo. And we can see also here some specific about Tenerife, that is one of their 5 qubits computer. They are very, very good computer right now, and is one of the only company that allows the public to use their computer for free. Okay, but you know, you see that they are not free of errors, of course. Second startup that I want to mention is Rigetti. Rigetti is an American startup born in 2013 in California. They are creating their own quantum computer with superconducting technology. They have 8, 9 machines, different models. The most powerful one is Aspen 9, that has 32 qubits, and they announced that they are close to building a model with 128 qubits. This is, for example, the topology of Aspen 9, and the lifetime and error gates, the median fidelity of the gates applied on this particular quantum computer. The third one that I want to mention is the D-Wave Quantum Computing Society. D-Wave, the quantum computing company, pardon. D-Wave is a particular example. Among all those we have seen so far, it is undoubtedly the most particular because they don't produce a general purpose quantum computer, but special purpose. This is, I think, the only company that produce quantum annealers. What does it mean? In practice, it means that they did a choice. With their computer, it is not possible to use and to implement all the quantum algorithms that we have in literature. Their computers are made with the sole purpose of solving optimization problems by implementing a particular algorithm called quantum annealing. We will talk about it Wednesday with the quantum annealing lesson. With this choice, they have shown that it's possible to make a grid chipset already. Their latest model has, in fact, more than 5,600 qubits. So very large computer, but we cannot use it to program with quantum computer that I showed you before this morning, but you have to program it in another way that I will show you Wednesday. Okay, so this is something about the wave. Okay, so superconducting qubits are macroscopic qubits. We have a very large experience with this kind of qubits. They can perform a fast operation. But on the cons, we have very low coherence time, low fidelity on gates, and they need to be cooled down. Okay. So let's see very quickly another implementation, and we will finish it maybe Wednesday. This another implementation, another qubit realization is the neutral atoms qubit technology. Okay, to date, the only technology that can be considered mature is the superconducting technology. All the other that we'll see here are in a more or less experimental phase. So, for example, in the case of neutral atoms, we are really close to implementing a general purpose quantum computer, but they are still working on it. Qubits neutral atoms are rubidium atoms, which can be manipulated through the use of special lasers. So with neutral atoms, you can use laser to create a topology that you create, the topology that you want. It's not a fixed topology, but you can adapt it to your problem. And to create connection between qubits, use exciting a particular atom and creating a sort of radius, that is the right radius, that can be used to interact with the other qubits. Okay, this is the most important company that is using this kind of qubits is Pascal. Pascal is a French startup that we have we have collaboration with, also with the Wave. Pascal is a French startup that is born in Paris since 2019. This is a spin-off of the Institut Optique. And in his team, there are the greatest experts in quantum computing using neural atoms in the world, maybe. The company was born after demonstrating the effectiveness of the qubits with a working laboratory prototype. In this first phase, the Pascal quantum machine is a machine capable of making analog calculations. We will show in a little bit what is it. In other words, it's not possible to program it as ITQC, but it can be used to simulate the evolution of particular Hamiltonians. The plan is to have a computer with 100 qubits by September of this year, and to increase the number of qubits to 1,000 to 2023. Right now, you cannot manipulate Pascal qubits with a digital processing, that is one of on the left of this slide, but you have to use an analog processing, that is the one on the right. Okay, this is the analog processing is something that you do acting on all qubits at the same time. Okay, so you create your problem and you let evolve it, acting on all the qubits at the same time. Perfect. So last thing, and then we will resume from here. We will resume from here if you want. Is the fact that the neutrons have a good coherence time. They have interchangeable topology, and they can work at room temperature, the qubits. But you have to cool down lasers. Okay. Cons, they are experimental technology. Okay, so let me say to you just 2 words about emulation of quantum computers, and then I will leave the floor to yeah, perfect. Then I will leave the floor to Marco Ballarin that will show us a particular way to emulate a quantum computer on a classical supercomputer in order to optimize the resources that we can use. So, what is emulating quantum computers? Emulate a quantum computer means recreate a quantum algorithm or a quantum circuit on a classical computer. It is possible, okay, but it's a little bit hard because emulate a quantum computer requires a considerable amount of resources, especially if you want to simulate a fair amount of qubits. Let's make some math here just to have an idea. Just consider that only to store a qubit register, we need 8 bytes for the coefficient, 4 bytes for every coefficient. We have 2 coefficients. We store it, the 4 byte in this case, the double, but maybe we have to double it if we want to use complex number. But we can use 4 bytes for a single coefficient, 4 bytes for the other one, and 2 bits for the state. Okay. Okay, so this is for a state composed of 1 qubit. For 2 qubits, we have to use the same thing, but for a state composed of 4 terms. 3 qubits, 8 terms, etc. At the end, we see that the number of bytes that we need to store a quantum register on a classical supercomputer is 8 times 2 to the n bytes. And this is a very big number, because if you see in the graphic near to the graphic in this slide, with 10 qubits we need 8 kilobytes of memory, 20 qubits, 8 megabytes, 40 qubits, we need 9 terabytes of RAM, 40 qubits. For 60 qubits, we need 9 exabytes of RAM. This is a very, very large quantity, okay? Furthermore, the emulation of a quantum circuit requires computational time, so another thing, for the application of quantum gates, because if the quantum gates has small matrices, it's good. But see, if I have to apply a very big matrix, a very big quantum gate, or a very big circuit composed, I don't know, of 30, 40 qubits, it's a very hard task, and I have to use a lot of HPC techniques to speed up this calculation. For example, with Marconi 100, this is our most powerful supercomputer. What we can do is we have 980 nodes, every node has 256 gigabytes of RAM. What we can do, we have 2.5 0.2 petabyte of RAM. 0.2 petabyte of RAM, we are between 40 and 6, between 40 and 50 and 46, something like that. Not anymore. Okay? So now we leave the floor to Marco Ballarin that will show you how to emulate a quantum computer in a smarter way. Thank you, Marco. The floor is yours.
You're welcome.
Thanks a lot.
And maybe Alexei has a question. I saw him raise his hand.
Yes, okay, of course.
One other question, pardon me, Daniela, was about what very low fidelity means in terms of order of magnitude. Could you give us some sort of an idea, please?
Fidelity has to be 100%. Okay, so any number lower than 100% is a problem, because also 99.99% means that in 10,000 of repetition, you make one wrong. And one repetition wrong means that your quantum algorithm is garbage. Okay, maybe it's not so. Maybe I'm too severe at this point of view, but I think that the fidelity has to be very, very high. Maybe you can use some quantum correction code, or you can use some particular algorithm that Riccardo will show you today or Tuesday, I don't remember, that are NISQ algorithms. Okay, those algorithms are studied to work also on noisy computers.
For what I know, if I may add something, I think that actually there is no study in that way, because we have small quantum computers, but the threshold for having a full tolerant quantum computation, I think it is at an error of 10 to the minus 4 or around that threshold. So your fidelity should be more than 99%, 99.49.
Thanks, Marco.
You're welcome. And are there any other questions, or shall I start with my...
Seeing here in chat.
I have a question. You told about topology of quantum system, and what does it mean? What does it mean? The connection between, for instance, qubit number 1 and qubit number 3.
It's the fact that you can apply a quantum gate on them. You can apply a quantum gate on 2 qubits only if they are connected. If they are not connected, you have to do something else, like swapping states or maybe some other trick to make it connected in some way.
So it means that if qubit number 1 is connected with qubit number 2 and qubit number 3, but is not connected with qubit number 4, so I can do the operations with the first 3 qubits or not?
You can, in what sense?
If I can interrupt,
Yes.
Alexei, at the end of my presentation, we will see an example that focuses on topology, because it is something that is important for the simulator that I'm going to explain. So maybe it will become more clear after my part. If it is not clear at the end of my presentation, you can ask again the question. But I think that maybe with the examples, it will be easier to understand.
Okay, thank you.
Okay, so I.
Another question. Thank you, Marco. I will turn off my camera. Go on.
Okay, you see my screen now. It takes like some seconds to take the presentation, but I think you should see.
We see the loading
Yeah.
screen.
Okay. So simulate quantum computer with matrix product state. Let's. We have already seen it, but I think that a really quick recap will help understanding everything. So the computer we are using now is based on the classical bit, and we have seen that to pass to quantum computing, we have to pass to the quantum version of it, which is a qubit, which lives in a space that has a dimension 2, which means it can have two possible coefficients to describe the state, and it can be described by the block sphere, as Daniele explained to you this morning. But the fact is that we are not interested in one single qubit, but in two or more 6 qubits. And for 6 qubits, the number of coefficients needed is 2 to the 6, which is already 64. But in general, as we have seen a small time, the general dimension is 2 to the n. But to understand better what 2 to the n means, 2 to the n coefficients means, it's better to translate it in gigabyte of memory. So we have, if we put ourselves in double precision, so with the 64 bits, we have complex numbers, so we have to use 2 double precision numbers for each coefficient. Then we pass from bit to byte, dividing by 8, and from byte to gigabyte, multiplying by 10 to the minus 9. And then we have this dimension of the Hilbert space, which means the number of coefficients, which is 2 to the n. We can see on the right, on a logarithmic scale on the y-axis, the number of gigabyte needed for storing the state. And we see that for storing a state of 50 qubits, we would need 10,000 tera of RAM, which is really an astonishing quantity of memory. And so it seems that simulation are not feasible, but still they are important because they let us make checks on the experiments and understand which are the meaningful future development in the fields, at least now when we do not have fault-tolerant quantum computation. In fact, the checks on experiment would make us understand when we will have fault-tolerant quantum computation, so when the computation can be relied consistently, and when we reach quantum supremacy, which means when the computation we do on the quantum computers cannot be reproduced classically. On the other hand, the future developments means we can try quantum algorithms to see if they are really worth the effort of developing them. One example, which will be explained, I think, tomorrow, is the quantum Fourier transform, which is the quantum version of the classical Fourier transform, or quantum machine learning. And as I said, to really understand and go deeper, we need to perform classical simulation of quantum computers. One possibility would be to make exact simulation using software like Qiskit, which will be explained tomorrow and very briefly used today at the end of the presentation, which is an open source library from IBM. But we have seen that it is not feasible for a large enough number of qubits. The other possibility is to use tensor network methods. They are an efficient way of compress information about our quantum state by bounding the entanglement of the system, by bounding its quantum power from a certain point of view. But this enables us to simulate really a bigger number of qubits, and so even understand the scaling behavior of algorithms, for example. So if we want to understand what are tensor network methods, it is first of all important to understand what are tensors. So we will use this graphical notation here because the mathematical notation becomes really cumbersome really quickly. So a ball is an order 0 tensor and actually represents a scalar number, while a ball with a single line is an order 1 tensor, which is a vector. A ball with 2 lines, I think you start understanding, is an order 2 tensor and actually a matrix. And so we can go over and generalize this definition to any number of lines to obtain an order n tensor. Like this one, in this case, we have 4 lines, so it is an order 4 tensor, and we can call these lines legs of the tensor. So what is really important is that we can perform many manipulation on the tensors. One example, we can reshape their indexes, their legs, as we prefer. So if we start from a vector like this one, we can actually reshape it into a matrix without losing informations about the original tensor. But it may be more useful for some particular task. So what is very, very important is that this possibility of reshaping tensor means that a tensor of any order can be mapped into a matrix. So we can use linear algebra, which are algorithms that are really efficient and optimized on classical computing to work with tensor. So if we have this tensor, we see a tensor with 6 legs would already have 6 indices, and making a mathematical notation would become really difficult quickly. We can reshape the tensor by merging together these 3 legs with the green circle and these 3 with the yellow circle, and actually from this order 6 tensor we can pass to a order 2 tensor. It will still have the same number of coefficients as we are seeing here. We pass from 4 to 4, but it will be in the form of a matrix. And we can perform several operations on tensors using the graphical notation introduced. For example, for order 1 tensor, we can easily introduce the complex conjugate. So if a complex vector at this point is a ball point with the leg pointing downward, its complex conjugate is the same ball with the leg pointing upwards. Then there are other important operations, and one of the most important one is the contraction between 2 tensors along their legs. We start with order 1 tensor because it is simple. It is equivalent to the scalar product between 2 tensors. So here I'm using the Dirac notations with bra and cat. We see that making this scalar product is equivalent to writing this scalar product. Be careful, since psi is a bra vector, it means that it is the complex conjugate of its elements. But we can write this expression easily with the graphical notation we had introduced in this way. And if you look at it, it becomes more meaningful because since we are contracting on this leg, it means that once the sum is done, this leg no longer exists and these 2 tensors are merged together. And in fact, they become a single tensor. And notice, we know that the scalar product between 2 vectors is a scalar. And also the graphical notation let us understand it. Contracting this with the other will lead to a scalar. And then the contraction between order 2 tensors is simply the matrix-matrix multiplication. And we see again the importance of the graphical notation, since this link gets merged between the two tensor, and as we know, the matrix multiplication of two matrices is an output another matrix, which is the multiplication of the two. If you have any question, just interrupt me, open your mic, and ask me. Then we go on and understand the general contraction between two order n tensor. As I've said, if we would use simply this mathematical notation, it would become cumbersome. This is just one contraction, and we already have a sum over three indices of the two tensors. But using the graphical notation is really easy and intuitive. We see there are two free legs and three contracted legs, as we have there the three indices that are contracted through the sum. And when we contract, these three indices goes away because they are sum up, and we end up with an order 4 tensor, which is the same result that we would have performing the sum. But in practice, the simulator, the computation are not done in this way, but in a more clever way. So we take the same two tensor we had here, and we regroup the indices following the colors. So we regroup the three indices of T1 in green, the three indices of T2 in yellow, and the contracted indices in red. By reshaping them and merging them together, we obtain actually a matrix multiplication. Because you see, this tensor has two legs, this tensor has two legs, and one of them is contracted. So we can use all the matrix multiplication subroutines and functions that are highly optimized on supercomputers. And then we perform the matrix multiplication and reshape back the tensor by separating again the green line into two legs and the yellow line into two legs, obtaining the same tensor we had here. One last thing of, let's say, tensor operations that we have to understand before going into the actual quantum simulator is how to separate two tensors. And in particular, it is done through a singular value decomposition. First of all, we have our tensor. We can reshape it as we wish. For example, since up to now we have only seen shaped together legs that were adjacent, here we can see it is not mandatory. We can merge together legs that are not adjacent in the notation. So we pass our general tensor to a matrix, and then we use the singular value decomposition, which is a linear algebra techniques that let us write an arbitrary matrix as the product of U, S, and V, where U and V dagger, where the dagger is the adjoint, which means the transposed complex conjugate. U and V are unitary matrices, while S is a diagonal matrix. So we have this change here. We pass from our T3 through to US V dagger. And you see I have represent S as a square, since it is a diagonal matrix, a diagonal tensor if you want, or a diagonal order 2 tensor. Then we contract S with V dagger, and so end up with two matrices. This, by the way, is a really efficient contraction, since S is diagonal, and so as not a as a linear number of non-zero elements, the diagonal 0. And then to obtain two tensor again, we reshape them, these two operations, these two matrices, we reshape them in the original tensor operator. I understand that it can be a bit difficult, so this is a quick recap on how the separation of a tensor works using the SVD. So we have our tensor, we make it a matrix, we apply the singular value decomposition, we contract the diagonal matrix into the right one. Actually, this is an arbitrary choice. You could have contracted S with U without any problem. And then you reshape it, coming then to having two tensor, in this case, two order-free tensors.
One question.
Yep.
When you do your SVD decomposition, what happens if some of the diagonal elements of S are 0? Does that probably mean something about the qubits?
Yeah,
and is that a problem? Is that a problem for the calculation? Thank you.
Totally on the other side, we will see that in a couple of minutes, but having 0 element in the diagonal matrix is actually something which is really useful. But we will arrive at it in 2 slides, I think. So let's come back to our initial goal. So representing a quantum state in an efficient way. A quantum state of n qubits can be represented as a vector with 2 to the n coefficients. So using our notation, it is simply this ball with a leg, which has 2 to the n possible values. But we know that we can reshape this vector in a tensor form. And so we reshape it to be a tensor with n legs, 1 for each qubit, and each leg can have 2 values, 0 or 1. This is the general expression for a quantum state. You see the S, sorry, my dog is yelling. The states S1, S2, Sn are the possible values of the qubits, so it can be either 0 or 1, and C are the coefficients. It is simply a compact way of writing what we have seen with Daniele. So now that we have our tensor, our big tensor of our quantum state, we can apply iteratively the separation on this tensor using the SVD. So we group together the first qubit and all the other. We end up with a matrix. We perform and you see, here we have 1 qubit and here we have n-1 qubits in this single leg. We perform the separation, and so we have one tensor which now only describes the first qubit, and a big tensor that describes the other n-1 qubits. Well, now we perform this operation again. We merge together the yellow indexes. So this index here, which connects the first qubit to all the rest of the system, and the index of the second qubits, and then the index of the remaining n-2 qubits, as we see here. And again, perform the separation. This iterative procedure will actually let us arrive to a tensor network, which means several tensors which are connected together, where there are n-2 order-free tensors like this M2, and 2 order-2 tensors at the boundary, like M1 and Mn. For the sake of notation, since S1 actually is linked to the state of the qubits, to the actual physical state of the qubits, it will be called the physical index, while the links that connects the single tensors together will be called auxiliary indexes. Sorry for the typo. But up to now, okay, we have a fancy way of representing our state, which divides the full state into a tensor for each qubit. But we didn't earn nothing. I mean, we are, as we have seen at the starting point, we are using the same number of coefficients now, and so we have no actual gain from this procedure. We still have 2 to the n coefficients. So I was putting something under the, well, I hadn't said something important, an approximation that we do in the separation and that some of you highlighted before, which is a truncation. First of all, we introduce a bond dimension of the system, which means which is this chi-max, and denote for notation with S1 the greatest eigenvalue of S, which is the singular value matrix. Then, when we actually make the SVD, we make a truncation. What do I mean? I mean that if that S prime is defined as Si, so the eigenvalue, if the eigenvalue over the largest eigenvalues of S is lesser than a certain threshold, and if I is less than the bond dimension, which means that we are only keeping chi-max eigenvalues of S, not on all the eigenvalues, only chi-max. It is really important. So let's understand what actually does this two approximation means. We keep only the eigenvalues that are big enough. In this way, we neglect the subleading term for the state description. What does it mean? I mean, like, let's say we have an eigenvalue which is 10 to the minus 1, and then another eigenvalue which is 10 to the minus 10. The eigenvalues which is 10 to the minus 10 really doesn't have a lot of importance in the description of the state, since we have a much higher eigenvalue. And so if the ratio is less than epsilon, this threshold, we simply do not take into account them. We neglect them, saying, hey, they are not important to our state. And on the other end, we keep only the first highest chi-max eigenvalues. This is really a more strong approximation than the previous one. This is a brute force approximation that let us keep the number of qubits high. This may be, as I have written here, a strong approximation because actually we may throw away important eigenvalues in this truncation, but we may also not doing that. So it is on the other way. This is a parameter that can be tuned to obtain a correct, a good enough output. But this let us keep low the error. Also, let us think about it. If our state can be defined by few enough eigenvalues, because a couple of them are different from 0 and all the others are equal to 0, then we can put a high bond dimension, let's say 10, and make our computation, but still describe the state really well because of this approximation here.
Question?
Yep.
Marco,
Go
I'm
ahead.
sorry. My question was originally, how do you set Chimax? But you partially explained just now. However,
sorry, go ahead.
yes. However, it seems like, it just seems to me that, because I don't understand exactly, that you set Chimax as a function of the eigenvalues in the diagonal of S. I'm a little bit confused, I'm sorry.
No, maybe I didn't explain me really well. It's not a function of the eigenvalues. There are a couple of ways of setting Chimax. One possible way is to set it high enough that you should be able to describe the state well. Let's say you put it at 100, and then you simulate your state for smaller values of this bond dimension here. Once you have your state at an high bond dimension that you are quite sure has a correct description of the state, and then you have your state with a bond dimension, let's say 3, which you are unsure is a good description. You simply then take the fidelity between these two. If they are similar, if the fidelity is high enough, it means that 3 is a good enough bond dimension as much as 100. If instead you have a low bond dimension, a low fidelity, it means that you are performing too much of an approximation, and so you should use a higher bond dimension. And you can make iteratively this procedure to understand which is the correct one to use, which is the smaller bond dimension that let you describe correctly your system.
And would that apply to a computing system as a whole, or just to one operation at a time?
You usually set it for the whole simulation, so for the whole computing system, not only for a single SVD. It is okay. I have answered you, or you
yes, thank
further...
you.
Okay, fine. So by introducing this truncation, it means that each one of our tensor in the tensor network, which has the particular name of matrix product state, has at most dimension Chimax by Chimax by 2. And Chimax, as I said, is the bond dimension, and we can say that it controls the amount of entanglement that our system can represent. As I've said before, the higher the bond dimension, the more states we can describe exactly. But it is not sure that we cannot describe exactly states using a low bond dimension. For sure, we cannot describe exactly random states on the Hilbert random quantum states. What I mean by random quantum states, if you choose each one of the coefficients of the states at random, then the matrix product state is not a good way of representing your state, of simulating your system. But since we are usually interested in some specific states, then matrix product states are really useful. And in particular, because the number of coefficients scales linearly with the number of qubits and quadratically with the bond dimension, which means, as we can see in the right plot, on this plot here, that with a bond dimension of 10, for example, which is low, we can simulate 50 qubits with less than 10 to the minus 3 gigabytes, which means with less than 1 megabyte of RAM. And even increasing the bond dimension, and I can assure you that 10,000 of bond dimension is really a huge one, we can describe 50 qubits with far less memory, with far less RAM. Then now, up to now, we have seen the evolution of this, only the storing of the state in the RAM, not its evolution. Here we understand how we do it. The important thing is that we start from the void state, the 0000 state. As Daniele said before, most, if not all, of the quantum algorithm are developed such that you start from this state. This state is called a separable state, and that means it has no entanglement. It is a classical state, let's say, and it means that it can be described exactly with an MPS with bond dimension 1. So we really do not need a high bond dimension to describe the starting state. And then we apply gates to evolve the state, as we have seen the quantum circuit formalism. We have two limitations with matrix product state simulation, which are quite important. The first is that we can only apply 1 qubit and 2 qubit gates. Actually, it is a limitation, but it is at the moment the same limitation we had in the hardware. I don't think, I'm not really sure, but I don't think there are hardware which implements 3 qubits gates at the moment. And the other limitation is that we can only work with a linear topology. So qubit I is only connected with I plus 1 and I minus 1. But let's see the evolution. First, we have the application of 1 qubit gates. I will represent the gates as squares. Here, for example, we have an Hadamard gate. You see, they act on a single qubit. They are single qubit gates. But this means that they do not introduce entanglement in the system. They do not make quantum correlation between different qubits. And this means that they do not change the bond dimension. So if we would have quantum circuits with only 1 qubit gates, it wouldn't be really interesting. It would be trivial because it would be easily reproduced classically. But we could represent it with the bond dimension 1. Then we had 2 qubit gates, and its application is a little more involved, but we know everything to do it. We have these two tensors, which represent qubit I and qubit I plus 1. We apply a 2 qubit gate, for example, a CNOT. We contract the qubit. So we contract along this line, and this line, obtaining an order 4 tensor, and then we split it back to obtain again the 2 qubits. So knowing how to split the tensor, it is really a simple procedure. What is important is that now we are introducing correlation between the 2 qubits, we are introducing entanglement, and so the bond dimension will increase up to the maximum that we have selected for our simulation. So we can start from a bond dimension of 1, and applying 2 qubit gates, this bond dimension will increase along our matrix product state. So there is another subtleties that I will explain a little quickly because it is not, I don't think it is important to go into details of this, but I think it is also important for you to know that it exists. The truncation that we did obviously induces an error, and we want to minimize that error. To do so, we have to set the orthogonality center of the tensor network. In general, it means an orthogonality center is defined in this way here, but I prefer to give you an intuitive definition rather than the formal one. And so if I will denote the orthogonality center as our usual tensor, but with a red edge. A tensor A is an orthogonality center of the network if, when you contract the MPS with its complex conjugate, then all the other tensor on the left and on the right contract to the identity, which means that making this operation is equivalent, which is a global operation, you see, we take into account the whole qubit, the whole system, is equivalent to doing a local operation, which is this one. You see, this contract to the identity and becomes simply a leg. This contract to the identity, it becomes simply the other leg, and then there is the leg in the middle. So another thing which is important is that MPS are not only efficient in simulating quantum circuits, but let us measure interesting quantities. For example, we can compute the expectation value of any observable. Maybe this part will be a little clearer to physicists, but an observable can be a gate, so we can compute the expectation value of that gate over the qubit, which means basically making this operation here, where psi is the quantum state, gi is the qubit / observable we want to compute, and psi is always the quantum state. And taking this, since we can put A as a center of orthogonality, again is a local operation which is highly efficient. I just remind you that A is chi by 2 and G is 2 by 2. So we are actually making some matrix multiplication which is really manageable. And another thing that we can measure, which is really important, is the entropy between two partitions of the system. And from properties of the MPS, it is simply obtained in this way. So we contract two qubits together, then we separate them, and using the singular values here, we can compute the entropy of the von Neumann entropy, which is equivalent to the entanglement of the two partitions in this way. So we have a measure of how much, let's say, this half of the matrix product state is entangled with this other half, and can be really important when developing quantum algorithms. Then the other thing which is really important is the fidelity. Why it is so much important? For the thing that your colleague asked me before on understanding which is the correct bond dimension to use, because we can simulate psi with a bond dimension and phi with another one which is higher, and then take the scalar product between them, which is simply this one, and using the sorry, here there is a small error. So before giving you the slides, I will correct this. This is not true. This equal sign is not true because the center of orthogonality is defined for a tensor network. So this would be true if it was psi-psi, but being a different MPS, M4 and N4, for example, does not contract to the identity. So this is not true, but still it is a efficient way. It is efficient. And then we can perform projective measurements. So, for example, from this circuits, we can perform the projective measurement and measure 0, 0 with probability 1/2 and 1, 1 with probability 1/2. Which is important since we usually have projective measurement at the end of quantum algorithms. Finally, let's go back to our problem, which is the linear topology. What does it mean? It means that, for example, these circuits could not be simulated on matrix product state simulation. Why? Because Q0 and Q2 are not adjacent. So this C0 gate cannot be applied in this way. But we can use swap gates and linearize it. So you see, the first part has no problem, and it is repeated. Then we have the swaps gate. So qubit 2 goes into the place of qubit 1. So here, let's say we have qubit 2, then we perform the control knot between qubit 0 and qubit 2, which is the same as here, and then we bring back the qubits in their correct alignment. And this is done in a dumb way. So we put our qubit in the correct place, and then we put them back in this original place. And this is good because it is a very simple circuit. But more complex circuits may have better strategies, and there are algorithms that actually minimize the number of swaps to map an arbitrary circuit to a linear topology or a given topology in general. Does this answer the question about topology that there was at the start of the presentation, before the beginning of the presentation?
Well, I see. So it means that if I have qubit number 1 connected with qubit number 2, it means that I can do a direct operations between them, right?
Yeah,
and
exactly.
If it is not connected with qubit number 3, I cannot do like H or the next one.
Yeah, exactly. As you see, Q0 and Q2 are not connected, so this operation cannot be done. And so we decompose it into this free operation instead.
So in a real quantum computer, we also need these operations, right?
Yes.
You
Exactly.
mean, okay, thank you.
It is not, yeah, it is a limitation of a matrix product state, but it is also a limitation of real computers. Actually, there is a thing which is important to take into account, which is that more gates means more error, and for real quantum computers, a longer implementation time, which will lead to the decoherence processes that Daniele explained before. So if you have to perform an algorithm on an hardware or on MPS, it is better if your circuits already takes into account the topology. But if it is not possible, then we can map it.
Okay, thank you. So for me, the last thing to understand about this question is how it's possible to make physically make the connection between the qubits and why it is so difficult.
Well, I'm not really an expert on the hardware point, but let's say that it involves a lot of optimal control of quantum objects, which is really not easy. And well, I cannot answer your question in a really good way, but maybe I will search for something in the literature and make it available.
Okay, thank you.
So, what is really good about the MPS simulator, as we have seen before, is it is highly efficient in particular cases. So this is a plot of a simulation made on Marconi 100, which is the supercomputer of CNECLA with 980 nodes, 32 cores for each node, and 256 gigabytes of RAM for each node. I ran personally this simulation. The first one is the exact simulation using 128 threads and a multi-thread simulator from Qiskit. You see, this point is a number of qubits of 30 qubits. And we are performing a quantum Fourier transform, which is a quantum algorithm that has a number of operations which scales quadratically with the number of qubits. Just to have an introduction. And it is really, well, it is behaving exponentially as expected. We are in a log-log scale to better see the power law behavior with the number of qubits of the MPS simulator, which I developed. And you see here we are able to simulate a quantum Fourier transform on 300 qubits, which would need 10 to the 79 terabyte of RAM if we would want to make the exact simulation. It is not feasible at all, but with MPS we can do it. A small note here, the maximum bond dimension was 10 to the 4. However, it was not reached. I think that the bond dimension that was necessary to correctly describe the state was under 10. So even with small bond dimension, we can correctly describe very difficult states. What about future developments of this technology? Well, we can try to tackle problems of quantum supremacy and understand if they really are quantum supremacy. This type of simulator of MPS can be easily generalized to photons, and so we can try to understand if the quantum computation advantage from the Chinese group is really unbeatable, is really quantum supremacy, or maybe we can still simulate it classically well enough. Or we can try to understand which is the, for real, the fault tolerant threshold after, by using quantum error correction codes, since we are able to simulate a much higher number of qubits that it is available at the moment. or even more, we can make some simulation of and some trials of quantum machine learning and understand which is the entanglement in the circuits used for quantum machine learning, how does it scales, and if using more qubits we are able to obtain results that are similar or better than the classical machine learning part. So I finished my presentation, and I would ask if there is any question about anything that I described, that I explained up to now.
Does the precision of calculations suffer on approximation introduced in MPS?
Yes, it does. I mean, if you use a low bond dimension, then you would not be able to correctly describe your state, and so you would have a low fidelity with your target state, and that's not what you want. But using that procedure by modifying the bond dimension, let you understand which is the correct one that can be used.
But in this sense, related to this question, the bond dimension is or isn't related to the quality of the hardware you're using, in the sense that I understand it describes how related various states are in your system. And if states are related in the system in a way that is spurious or that you don't want, maybe could hardware actually induce a lower bond dimension than the one that would come out directly from analyzing your computational system? That's my question, I guess.
Okay, I'm not sure I understand it correctly, so I will try to answer and then say me if I misunderstood something. So you're asking if the bond dimension will be influenced. No, sorry. I will ask you to repeat your question. And do you intend with regard to the real hardware?
Yes. I understand that bond dimension is related to how various states are related, and maybe I forgot the term you use.
Entangled?
Term. Entangled, yes. I tend to think intrication, but it's entangled. This entanglement can come from your computational system, how you pose the problem, what type of problem you're trying to solve, but it may also, as I intuitively see it, maybe wrong, it may also come from the hardware that introduces some sort of a correlation of states.
Okay, so, I got to your question.
Okay.
Actually, entanglement is one of the most difficult quantum resources to be done, to construct, to build. So it is very improbable that 2 qubits in your real hardware will get entangled while you don't want them to. It is really difficult to entangle 2 qubits, and so it is improbable that it happens by happenstance.
Okay, thank you.
You're welcome. Any other question?
Okay.
Okay, so try it yourself. If we have time, I don't know. I'm not seeing the...
Yes, no, I just realized that we skip a pause. I'm sorry, we skip a break of one. So yes, we have another 10 minutes and we can finish 1/4 of hour before the 5 p.m. So we can
okay.
restore the break. I'm sorry.
I apologize too for robbing you of your break. By the way, try it yourself. So I prepared a little Jupyter notebook to take a grasp of these concepts. It is really easy and does not have a lot of the possibilities that should be available in MPS. For example, well, let me go here, which is the presentation with all the slides already completed. There is no possibility of taking scatter products or other things because this simulator is built with another purpose rather than all the measure that I've shown you. But I don't know how much can I say about it, but maybe in the future Cineca will have a simulator that can do all these, which is optimized for Cineca resources. I don't know, Daniele, how much can I?
Yes, you can say, yes, you are working on an emulator like that we will install on Cineca machines. And then everybody, if you want, you can simulate a lot of qubits with our HPC systems, but it's still under development. But we are working to install it, to realize an HPC version and installing it.
And the most important part is that you will be able to access all the measures, all the measurements that I have explained, and many more that maybe I missed or that I intentionally left out of the presentation to take the presentation time into the bounds. So I invite you to take the Jupyter notebook that is inside the folder that Daniele before showed you and explained you how to install. For those that are auditors and do not have access to the Cineca cluster, as I've said before, I invite you to download the notebook from the GitLab. It is very simple. You can go to the link that Daniele sent before, which should
copy it again on chat.
You should bring you there. Then you click on MPS Jupyter, MPS simulator.ipython notebook, and here there is the download button. So you can download it as simple as that. Then to run it, actually, you need a Python environment with a Qiskit, but yeah. At least you will have it if you want to try it at another point. So,
yes, Marco, I'm sorry,
yep.
if I may add something to just what you said now for people who are not registered student completely. If they want to install the Jupyter notebook, they have to install Qiskit, NumPy, and Matplotlib. And as Daniele mentioned this morning, this is best done in a virtual environment. And I've made some tests because I was doing two things at the same time. And the best Python version for this, for me, it was 3.7.0. So virtual environment Python 3.7.0, and you install Qiskit, NumPy, Matplotlib, and it works.
Also 3.7.3 works well.
Okay.
Yes, I've uploaded the slides on the webpage of the course, and there is also the instruction to install a virtual environment for the Jupyter notebooks for the next lessons. So if you want to go to maybe let's wait. This is 10 minutes, but you can download the slides with instructions for installing your virtual environment. slides.
About the slides, do not download, if they are available, do not download MPS lecture slides, because I have to correct that small thing or one of them, and then they will be uploaded and then corrected.
Okay, I will wait for you for uploading it.
Thanks, Daniela. So we have our, do you see it well? Do you want me to zoom a little? Like, for me, it's the same, so maybe this is better. I assume it is better. Okay, we start really easy. We start with 4 qubits, a small number that can be easily simulated by a classical computer. I mean, we have 2 to the 4, which means 16 coefficients. It's really easy. Then we create a very simple circuit, which is a GHZ state, which is simply a generalization of the bicouple. So the bicouple was 0, 0 plus 1, 1. A GHZ state is n zeros plus n ones. The circuit has already been, sorry about one thing, you will understand Qiskit tomorrow. I know I used it today, but it's only because it is the simpler simulator available. So by running this cell, you should have this output here, so which is the quantum circuit. You see H on the first qubit, and then a series of controlled knot that goes from the first qubit to all the rest, a barrier to keep things neat, and then the measurements. I put it here, this small clause, this small condition, just to not have circuits of 50 qubits to be drawn. Then we have the fact that I was telling you before. We can only simulate circuit with linear topology. So this topology here, which maybe it is not visible if you don't have the image in your folder. I don't know. Do you have this image on your notebooks? Well, yes, I will assume you have it. So 1 is connected to 2, and 2 is connected to 1. 2 is connected to 3, and 3 is connected to 2, and so on. A linear topology. We can say to Qiskit that we have a linear topology, and then make its optimized circuit linearize this circuit here. So by running the cell, we obtain this circuit here. It is different from the one that we had before, but we'll have the same output. And it is linearized. It is linearized really. Okay, this, for example, is more simple to look at. It is a stochastic optimization, so it should change each time you run the cell. But you see, what is important, it has been added some swaps gates to linearize the circuit, and it has increased the number of gates in the circuit from 9 to 11. In this case, we had only 4 qubits, so it is not a big increase in the number of gates. Then we decide our bond dimension. We recall that with chi equal 1, chi max equal 1, we can only represent separable state, which means with no entanglement. Nevertheless, we choose 10. And then we use Qiskit simulator for matrix product state, specifying the matrix product state maximum bond dimension. And we see, as expected, we have half of the measurement in 0 and half of the measurement in 1. But what does it happen if I put a bond dimension of 1? I mean, this state is entangled. And this means that I shouldn't be able to represent it using a bond dimension of 1. And if I run it, it is true. Using a bond dimension of 1, I obtain the wrong state. While using before the bond dimension of 0, I obtained the correct one. Now, just for the sake of doing it, let's say that the number of qubits is 50. There is no drawing since it was upper bound to 10. And we pass from 101 gates in the initial circuit to 194 gates. With the bond dimension of 10, it took less than a second to simulate 50 qubits. And still, with the bond dimension of 1, it does not work. Now, I would make you just 2 quick questions, even though my time should be finished. And they will be, which is the minimum bond dimension for which I'm able to simulate this state, and how many qubits are you able to reach in the simulation? If you want to play a little with the notebook, these are 2 really easy questions. You just have to change the value here, and you have to change the value here as you prefer. And well, after that, I've finished. I will be still here for questions for some time, for sure, at least until 15. But I think if there are questions, even a little more.
Could the answer, well, maybe I shouldn't, to your question was like 3?
Here, the bond dimension 3? Are you sure?
No, well, okay, I'll keep on.
Okay. 10 qubits seems to be the maximum.
Yeah, this is the maximum bond dimension.
So
and which is the minimum maximum bond dimension for which I describe the state correctly.
Okay.
The last answer was really close to the correct one.
One more general question, if there is time, regarding MPS.
Yes, I am totally.
So if I understood that correctly, you're basically thinking about how to use a classical computer to simulate our current quantum computers as efficiently as possible by exploiting the fact that the entanglement in those is limited.
Yes.
Have there been any efforts to maybe also take into account that the precision in the current quantum computers is also limited? To somehow use that to also simplify the classical computation, so that you only have to sort of keep pace with the imprecise, not 100% precise quantum computers that we have right now, rather than a theoretical one that doesn't make any errors?
I can link a paper discussed about it, but the main idea is that even if we are not able to describe correctly the state because we are not using an high enough bond dimension, then maybe we are still able to describe the state as well as the actual quantum computers. So actually, the fact that quantum computers now are making errors makes our life easier because we can lower the bond dimension and still have results similar to theirs. For what instead concerns errors like I don't know, putting gate errors, that is a work that is in the to-do list but has not yet been done, like making introducing the possibility for MPS to make an error in the application of the gates, like it is for the real computer, that there is the 1/10⁻⁴ possibility of not applying an Hadamard while in your circuit there is an Hadamard gate, for example.
All right, thanks.
You're welcome.
Okay. So, is there any other question? Unless I think that we can stop here.
Okay, so last thing, the minimum maximum bond dimension is 2 for the GHZ. So we can go up in the number of qubits really high because we only need a bond dimension of 2 to correctly describe this state, no matter how many qubits are there. 2 is enough.
Cedric has said key max equal to 2. Okay, perfect. So
I will stop sharing.
Thank you.
May I ask question? Is
Yes.
still the same problem? I cannot enter because it's waiting. I tried to relaunch 10 times. It's the same.
If it's saying waiting, you have to wait.
No. Local host contact waiting for reply, but possibly the problem is not. I'm not sure if the problem is on the supercomputer, but not in my computer. I'm not sure, and I don't know how to check.
In chat, Sergey wrote something that I will not tell you, but I think it may be a good idea.
I didn't understand. Okay.
Yeah, yes, of course, Sergey. As also Jorg is saying, you can, if you try again, if you try 2 or 3 times, eventually at the end you will use it. I tried every Jupyter notebook on every account and it worked, so there is no problem about permission or something like that. Okay, guys, thanks a lot. I'm happy it was a good day for you. It's a little bit hard, but very satisfying. Sorry for the inconvenience. It's the first edition, but we will improve very strong in the next year. Thanks a lot. And the slides of the course, I already said it, but I repeat, the slides are uploaded. There is a slide of the today's lesson and then the instruction to install Jupyter notebooks and, in case, virtual environment on your machines. So great, very good to see that you enjoyed the you mean you still have a brain? Little bit, something like that will move my body. And thanks a lot. See you tomorrow, and with Riccardo Mengoni that will show you some quantum algorithms and a lot of good stuff. Thanks a lot. See you tomorrow at 9 p.m. at 9 a.m. not p.m. And thanks. Bye bye.
Thank you also from my part to
Thank you.
everybody. I don't know if I don't think I will be there tomorrow, but if you have some new questions that you want to ask me, I put in the chat my institutional email so that you can have it, because I forgot. Or maybe I will put it also on the slides so that it will be available.
If you, when you give me your updated slides, I will update it on the website. Thank you. Thanks, everybody. It was really a pleasure. See you tomorrow. Bye-bye.
Bye.